Yeah. That's the way every day goes.
Good day everyone. In this presentation, we will be discussing about eigenvalue, eigenvector, and eigenspace. These three concepts are very important in linear algebra because they help us understand how we can transform vectors. First, eigenvalue are the scaling vector. They tell us how much a vector is changed or smudged. Second, eigenvector are the special direction that do not change direction after the transformation. And lastly, eigenspace. Eigenspace are the collection of all eigenvectors related to the same eigenvalue, including the zero vector. Let's explore them in more detail. Here are the objectives of our presentation. By the end of this presentation, we aim to have the following. First, we will explain what eigenvalues are. Second, we will explain eigenvector. And third, we will understand eigenspace. And lastly, we will show how to calculate them with a simple example. This objective will help us understand both the theory and the practical application of this important concept.
Okay, let's go to our first question. Consider the matrix A equal to 0, 0, negative 2, 1, 2, 1, and 1, 0, 3. For our first question, it asks us to find the eigenvalue of A and determine whether the matrix is invertible or not. Second, we need to find all the eigenvectors of A and basis for eigenspace. Okay, let's go to our first question. We need to write this step to solve the question where it asks us to find the eigenvalue of A. So, first of all, we need to write the determinant. And inside that determinant, we need to write the lambda times identity minus A equal to 0. So, we need to put it inside and expand it like, okay, we take the determinant. First, remember, lambda times identity. So, lambda, that leading variable 1, we times again it. And we will get everything leading 1, that leading 1 turn into lambda. And other not change because the other number are 0. So we will need to minus again the matrix we'll get for the answer. And so we will get this answer with lambda 0 and 2, then negative 1, lambda minus 2, and then negative 1. And the last row is negative 1, 0, and lambda minus 3. Remember, all of this is still inside the determinant and equal to 0. So, to make the determinant, this determinant loss, we need to use the cofactor expansion. We can use anything from row 1, row 2, or column 1, column 2. It depends on you. But for this case, it is easier to use the column 2 because it has 2 0 on both sides. So when you want to count it, it's easier. So when we solve the equation, we will get lambda equal to 2, and 1. So, is it invertible or not? The answer is yes. It's because as long as the lambda is not equal.
Now to find the eigenvector for lambda equals to 2, we substitute the lambda equals to 2 into the matrix of lambda I minus A from question A. And after we have substituted the lambda equals to 2 into the matrix, we solve the matrix using Gauss-Jordan. And after you solve it and it is no longer solvable, you transform the matrix into SLE form, which is x1 plus x3 equals to 0. To solve the leading variable from the SLE, we brought the x3 to the right side. which is now is x1 equals to negative x3. So x1 is the leading variable, while x2 and x3 are free variable, where x2 equals to s and x3 equals to t, whereas s and t are any real numbers. Hence, we substitute the s and t into the x equals to x1, x2 and x3. So we can get x1, x2, x3 equals to negative t, s and t, whereas s 0, 1, 0 plus t matrix negative 1, 0, 1. Then the basis for the eigenspace for lambda equals to 2 is 0, 1, 0 and negative 1.
Hello everyone, my name is Muhammad Hadif Hakimi. So, in this example, we find the eigenvector for lambda equals 1. We substitute lambda equal 1 into matrix A minus lambda I. Next, we perform row operation to simplify the matrix into row echelon form. From the simplified matrix, we obtain two equations. One is x1 plus 2x3 equals 0 and negative x2 plus x3 equals 0. Since x3 is a free variable, we let x3 equal w. Solving the equation give x1 equal negative 2w, x2 equal w. Therefore,
now let's move on to result and discussion. So for A, we already know the answer for lambda, for our eigenvalue, where lambda is equal to 1, 2 and 2. And the matrix A is invertible since the value of lambda are non-zero, or if you want to say it as lambda, none of the lambdas are equal to 0, meaning it's invertible, because for it to not be invertible, one or more of its lambda has to equal to 0. But thankfully, for this case, none of it is equal to 0, so the matrix A is invertible. And resulting to matrix A is not singular. Continuing on to B, first eigenvector is where lambda is equal to 1. We've already found the answer, x1, x2, x3, where x1, x2 is our leading variables, while x3 is a free variable. And then we found the answer, x1 is equal to simplify, if x1 is technically supposed to be x3, but since x3 is a leading variable, we can assume t. We can say that x3 is equal to t, so x1 is equal to negative 2 x3, x2 is equal to x3, and x3 we do not know, so that's why it is counted as a free variable, and where we say it's t. So honestly, for B, here we are wrong, so it's supposed to be w, but it's okay, I think. So okay, continuing on, but t is a real number, and then for the basis for the eigenspace for lambda equals to 1 is negative 2, 1 and 1. And continuing on to lambda 2, where eigenvector equals lambda, where lambda is equals to 2. You notice that there are two free variables compared to where the eigenvector is lambda is equal to 1, where x1 is a leading variable while x2 and x3 are free variables, so that's why there are r and s, which supposedly in our case supposed to be t and s and t, where those two are r and s, or t and s, are real number, where in this case there are two bases for eigenspace, which is negative 1, 0 and 1, 0, 1, 0.
in conclusion, This study helped us to understand the relationship between the eigenvalues, eigenvector, and eigenspace. Eigenvalues tell us how vectors are scaled. Eigenvectors identify the direction of the remain unchanged, and the eigenspace contain all the eigenvector associated with the same eigenvalues. These concepts are essential in linear algebra and have many real-world applications, including engineering, physics, computer science, mechanical learning, and data processing. Thank you. That's all from me.
The reference is taken from the book of Linear Algebra 1, the 11th edition, and also from Madam Susanna Wati.